very central problem in economics. We'll think about the problem. We're going to talk about profit maximization. This is, of course, a very central problem in economics. We'll think about the problem of how a firm should maximize its profit. There's a few considerations at the outset. First of all, as the firm increases its production levels, its production costs will increase. And also, with more of its good available on the market, the selling price will decrease. Now, these two effects interact, but it's not always clear how, so we have to do some mathematical modeling to find out. The overall question, the ultimate question that we want an answer to, is how should the firm maximize its profit? What level of production, how many items should it produce to maximize its profit? To mathematically model this situation, we have to think about several aspects, and one of them is the costs that the firm incurs in production. Obviously, making more of a good costs the firm more. We model this with a total cost function. This is usually denoted by TC for total cost, and it depends on the production level Q. So this is a function of Q which tells us the total cost of producing Q items. So here's a little example. In this case, the total cost has the equation 1,000 plus 5Q, and perhaps is being measured in dollars. In this case, there's what's called a fixed cost of 1,000, and each unit of the good costs $5 to produce. You can see that this models exactly that situation. Here's a more complicated example, example 2. It's more complicated because we have a quadratic rather than a linear expression for the total cost. This reflects a situation in which what we call the marginal cost, which is the cost of producing one more item, that marginal cost actually increases with production. We'll come back later to the concept of marginal cost. Here's an even stranger, more complicated example. This involves the exponential function. So these may or may not be realistic examples, but I'm going to use them to illustrate the mathematical modeling that we need to do. Related to the total cost are two important concepts called the fixed cost and the variable cost. And the total cost is the sum of these two. So what do they mean? Well, the fixed cost is the cost of producing nothing. It's, as it were, the cost of being in business in the first place. It might be fixed costs such as rental of premises or things like this. So the mathematical definition of fixed cost is it's the value of the total cost when the quantity produced is 0. So it's TC of 0. Think of it as the cost before production even begins. The variable cost, well, actually, we can define that quite simply. If we've now define the fixed cost, we can simply say the variable cost is nothing more than the difference between the total cost and the fixed cost. That's the easiest and most mathematically sensible way of defining variable cost. If you read textbooks in economics, which are perhaps not so mathematical, you might see fixed cost described as the part of the total cost function that doesn't depend on production. And the variable cost is the part of the total cost that does depend on production. But that's a little bit vague mathematically. So for our purposes, these are the definitions of these important ideas that we are going to use. Let's go back and look at the examples we had. In this first example, example 1, you can see that the fixed cost is indeed 1,000 because by definition, it's what we obtain, the number we obtain when we put Q equals 0 into the total cost function, and that's 1,000. And the variable cost, by its definition, is TC minus 1,000, which is 5Q. So this is fairly straightforward. Example 2. The total cost is 1,000 plus 2Q plus 0.06Q squared. When I put Q equal to 0, I get 1,000. So the variable cost is the total minus the fixed cost, which is this expression here. Looking at these expressions, you might be tempted to think, well, what's happening here is I have part of the function that is fixed and part of it that's variable. And these correspond to the fixed and variable costs. But we have to be a little bit careful, as the next example will show. If I look at this function here, then by definition, the fixed cost should be the total cost when I put Q equal to 0. Now, when you put Q equal to 0 into this expression, you get 500 plus 0 plus e to the 0. But remember, e to the 0 is 1. So actually, the fixed cost is 501. And the variable cost, by definition, is the total cost subtract the fixed cost, which is this expression here, which gives this formula. Now, that might surprise you, because you might think, well, why is the fixed cost not just 500? Because that's fixed and this is variable. Well, that's where this possibly vague definition of the fixed cost as the part of the total cost that doesn't depend on production doesn't really work. Because what it really means, the fixed cost, is the total cost of 0, which is not 500 here, but 501. So this may surprise you, but it demonstrates why we need an important and clear mathematical statement of what fixed cost is. We'll see further examples, but this, I think, these three are a good place to start. So we've talked about cost, and of course that's one side of the firm's considerations. The other side is revenue. And generally speaking, what's the profit a firm makes? It's the amount of money coming in minus the amount of money going out. So it's its total revenue minus the total cost. So it's TR, I'm going to use TR to denote total revenue, minus the total cost that we saw a moment ago. I'm going to use the symbol pi, the Greek letter pi for P. I'm going to use pi to denote the profit. Let's think a little bit more about total revenue. We've already thought about total cost. We've seen some examples, but how does total revenue come about? Well, if you think about it, the total revenue is the number of items sold times the price at which they are being sold. You get P, income of P, for each unit sold. So the total income is the number of units sold times their selling price. So it's P times Q. So the profit is TR minus TC, and TR is PQ. Now, the question, remember, and this is important, the question that we asked right at the start is, what value of the quantity will maximize the profit? To understand that question and to be able to answer it properly, we need to know how the profit changes as a function of that quantity Q. And there's an issue here, because this P, the selling price, might not be a fixed number. It too will likely depend on the quantity produced. We know that as the quantity produced is increased, the price tends to fall. That's the downward sloping demand curve. How do we generally determine the selling price and quantity sold? In general, it's not easy, but it's straightforward if the firm is what is called a monopoly. What is a monopoly? A monopoly is a firm that is the sole producer of its good. Nobody else produces the good. That helps us because the Q that appears in the demand equation is the total quantity of the good. Now, if this firm is the only producer of the good, then that Q in the demand equation, the total production of the good, is exactly its production level. Without the monopoly assumption, the Q in the demand equation would represent the combined production of a number of producers. And so we'd need more information about how it relates to our firm's individual production level. But if the firm is a monopoly, things are much simpler. The Q in the demand equation is exactly our firm's production level. That means that we can actually use the demand equation with the understanding and the assurance that the Q that appears in the demand equation is exactly the Q that we're modeling, namely our firm's production. Here's a little example. Suppose a firm is the only producer of its goods. So this phrase, only producer, should signify that it is a monopoly. And the demand equation is Q equals 500 minus 10p. So we can solve this demand equation, of course, to find P in terms of Q. Now, this is a subtle point, but it's the point I was making a few moments ago. In general terms, the Q represented by the Q in the demand equation would be the total production of the good of all the manufacturers. But when the firm is a monopoly, it's the only producer, and so this Q is our firm's individual production. So that means we can find the total revenue as a function of our firm's individual production Q by using this value P for the selling price and multiplying that by the number of units Q sold. So total revenue is P times Q. P as a function of Q, our firm's production, is given by the demand equation because it is a monopoly, and we get this expression here. So this expresses the total revenue entirely in terms of the key variable that we're considering, namely our firm's production level Q. So let's go back and continue the previous example now. So our firm is a monopoly. It's got this demand equation. And let's suppose that the total cost function is given by this expression here. So as we already observed, because the firm is a monopoly, the P that we use for the selling price comes from the demand equation, and we get the expression we had a moment ago. So the firm's profit is total revenue minus total cost. Here's the total revenue. Here's the total cost. And when you carefully simplify this expression, you get this. And I say carefully because you're subtracting a whole bunch of stuff inside parentheses here. And so when you do this, you have to be very careful that you subtract 1,000, then subtract 2q, and then subtract 0.06 q squared. Everything inside the parentheses has to be subtracted. But if we do it correctly, we get this expression here. So here is our profit function, and the question that we're asking is, which value of Q maximizes this expression? That's the profit maximization problem. Here's what the function, the profit function, looks like if we were to graph it as a function of Q. And you can see it does indeed have a maximum value here. And that's not surprising because looking at the expression for the curve, it's a quadratic with a negative squared term. So we know it's going to have an upturned U shape. So the question is, how do we find where this maximum value of the profit is? A few more qualitative observations I want to make about this example. The profit is negative to start with. Does that make sense? Of course it does, because the firm incurs costs even if it produces nothing. These are by definition the fixed costs. And yet if it's producing nothing, it's not making any revenue. So when the production level is 0, when Q is 0, the profit, which is the total revenue of 0, minus the total cost, which is the fixed cost, will be a negative number. As production is increased, the profit starts to rise. as we go up the curve. And eventually the profit just becomes zero and then starts to emerge into positive territory. This value where the profit becomes zero is often called the break-even point. It's the smallest positive value of the quantity for which the profit is zero. And so what we can say is that just after the break-even point, the firm actually starts to make a profit. Now, in this particular case, the profit continues to rise to a maximum, and then it starts to fall. The fact that it goes up and then comes back down is reflecting the fact that the more that is produced, the lower is the selling price which consumers are willing to pay. There's a trade-off between the quantity produced and the price at which it's sold. So our question that we want to answer is, how do we, in a situation like this, find exactly which value of Q maximizes the profit? This is a very simple, straightforward example, and we could use some fairly basic techniques, but we want to develop some fairly sophisticated general techniques